Hey everyone, welcome back. In this video, I'd just like to compute a couple more examples using integration by parts to compute some integrals that we haven't done yet, or we don't know how to do so far. So let's start with, and these are two very straightforward functions that you would hope that we would be able to integrate. So let's see how it works, okay? So let's start with this one. So yeah, it's going to be the integral of natural log of x dx. This is actually one that we don't know how to do yet, okay? We know that the natural log of x is the antiderivative of 1 over x. At least the natural log of the absolute value of x is the antiderivative of 1 over x. But we don't know the integral of log of x itself. So what we can do is we can apply our integration by parts formula. So I'm going to remind us over here that we have our formula integral u dv equals u times v minus the integral of v du. All right, and we have our method for choosing dv is just this word, right, detail, and we work from left to right to choose our dv. So this is exponentials, trig functions, algebraic functions, inverse trig functions, or in this case, there's nothing left but a log, right? All right, so in this case, what we can choose is we can choose our, because L is the last choice here, right? It means log. Then what we should actually do is remember that in the other direction, this word tells us this now becomes a made-up word going the other direction. That tells us how to choose our u, right? So what we should actually do is just choose our dv to be dx and let the natural log of x be our u. So our u is going to be natural log of x. Our dv is just dx, and then we can work with this, right? So then our du becomes, as we know, 1 over x dx, and if our dv is equal to dx, then our v is just equal to x, right? And we can put this all together, multiply these, subtract the integral this way, right? And we get that the integral of the natural log of x dx is equal to the x times the natural log of x minus the integral of x over x dx. But this is just 1, right? And the antiderivative of 1 is x. So we end up with x times the natural log of x minus x plus c. All right, and so this is the antiderivative of natural log of x. All right, one more that's very similar to this one. What if we want to find the antiderivative of the arctan function, arctangent dx? Well, same deal. Now our word detail, right? Notice that in general, when you choose your dv, you usually have more than one function to deal with here, right? So in our case, the inverse trig is again so far down the tail of this detail that what we're going to want to do on this one is choose the arctan to be u. And we're going to treat the a, right? We're going to treat this as though, I should have said more about this on the previous one, but we're going to treat this like this is 1 dx, and we're going to treat 1 like a polynomial. So 1's like an a, all right? And so we'll choose this to be our dv. So we've got our polynomial and our inverse trig function. The polynomial rules in the choosing of dv. And then we can do the same thing that we just did, right? So if our u is arctangent of x, then our du becomes what? The derivative of arctangent is 1 over 1 plus x squared dx. Our dv, in this case, is just dx. So that means our v is just x. And then, same deal, right? We multiply and we subtract the integral. All right? So, let's see what we get. We have then that the integral, antiderivative of arctangent of x dx is equal to x times the arctangent of x minus the integral of x over 1 plus x squared dx. And now we ask ourselves, can we compute this? We still have an integral to do, right? So we still have an integral we have to compute. And it turns out that this one is a good candidate for a u sub, right? Because we can make this be our u, and then we don't quite have our du. What are we missing? Well, we're missing a 2 up here to make that a 2x dx, so that means we need a 1/2 out here. Okay, but when we do that, then we end up with our antiderivative of arctan is x times the arctangent of x minus 1/2 natural log of 1 plus x squared plus c. All right, and this is the antiderivative of arctangent of x dx. All right, so these are two that are a little bit tricky in some sense, just because there's only one function, right? So we have to just treat the differential like it's just dx. But we can apply the integration by parts formula and get an answer to an integral that we did not know how to compute before we knew integration by parts. So that's very exciting and useful. And we will use integration by parts from now on through the rest of the semester and into the future and probably for the rest of our lives. Okay, so